Question 12a, part 1. For this one, if we can show that the derivative of f of x is positive, that will mean that it's increasing. So let's differentiate this function. We'll have to use the quotient rule. So derivative of the first one is just e to the x, and then multiply by the denominator. And then minus derivative of the denominator is e to the x, and times the numerator. And divided by denominator squared. So we're trying to prove that this is positive. Let's simplify this. So e to the x times e to the x is e to the x squared, or e to the 2x. Just remember, two negatives make that positive. And that cancels with that, so we're left with the 2 e to the x. And we can see e to the x is always positive. So the numerator is positive and the denominator is positive, so it's always going to be positive. So you could say something like e to the x greater than 0 and e to the x plus 1 squared is greater than 0 for all x, therefore f prime of x greater than 0, which means f of x is increasing. Part 2. Now the definition of an odd function is one where you plug in minus x and you get out minus f of x. So that's what we're trying to prove. You don't have to write this in your proof, but it's good to keep it in mind. So let's work out the left-hand side, and we'll just simplify it until we get that. So we plug in minus x there, we get e to the minus x minus 1 over e to the minus x plus 1. And then we got to turn this into something involving f of x. So the problem we have is that we've got all these e to the minus x's when we want to have e to the x. So e to the minus x is 1 on e to the x. So you could think of this as 1 on e to the x minus 1 on e to the x plus 1 if it makes things easier for you. And generally when you've got fractions in a fraction, what you want to do is multiply top and bottom by these denominators so that that kills all the fractions. So what we want to do is multiply that by e to the x and that by e to the x. So when we do that times that, that'll be 1. And then that times that is e to the x. And then we've got that times that is 1. And that times that is e to the x. Okay, that's looking much nicer now, because what we're trying to show is that it's equal to negative this. So negative e to the x minus 1 on e to the x plus 1. So we're almost there. You just need to say that, that is the negative of that. You could even probably go straight to saying that it's that, but just as an extra step to show how we got there, that's just negative that, and then you can take the negative out the front. And then say that is negative f of x. And I probably should have put this around the other way, so that that's f of x. Okay, and that's it. Part 3. So we want to think about large positive values of x. That means we want the limit as x tends to infinity of f of x, which is that. And the way that I would intuitively do it is I would think, okay, this is getting really big, so that minus 1 becomes insignificant. And same on the bottom, the e to the x is really big, so that's basically gone. We can ignore the minus 1 and the plus 1, so it's just e to the x over e to the x, which is 1. The way that they want you to show that, though, in New South Wales, is to divide top and bottom of this by e to the x. So we'd get 1 minus 1 on e to the x, and on the bottom 1 plus 1 on e to the x. And then this tends to 0 as x tends to infinity, and the same with that one. So you get 1 over 1, which is 1. Part 4. Okay, let's have a go at graphing this. Let's start by working out when x is 0, what is y. So if we plug in 0 there, e to the 0 is 1, and you've got 1 minus 1, which is 0. So that means it's going to pass through the origin. And from part 3, we know that it has that asymptote, that it approaches 1 for large values of x. And then in part 1, we showed that it was increasing. So it's just going to go like straight up from there into getting closer and closer to 1. And in part 2, we showed that it was odd. So if you could just like imagine rotating this 180 degrees, that's going to give that. So there we have the graph of f of x. Now for part 5, we just need to look at this and think about what the reciprocal is going to be at each point. So down here you're going to have 1 on negative 1, which is close to negative 1. And then as it gets closer and closer to 0, though, you're going to get big negative numbers, like 1 on negative 0.1, say, is negative 10, so it's going to shoot off down that way. So it's still got that asymptote, but very big negative numbers there. And then you're going to get the same sort of thing for the positive values, where when x is really big, you're going to have values close to 1 here, so 1 over that is also going to be close to 1. And then for small y values here, you've got like, I don't know, let's say that's y equals 0.01, you would have 1 over that would be 100, so it's shooting off to big values there. So that's y equals 1 on f of x. Part B. So we can just solve this with the quadratic formula. And I like to remember the quadratic formula in 2 parts. First, that the discriminant is b squared minus 4ac, and then that the solution is minus b plus or minus root of the discriminant all over 2a. So what I usually do is work out the discriminant first. So we've got the b squared minus 4a is 1 in this case, and then there's c. So let's square that. We'll have that bit squared. Twice that times that would be 12i. And then plus that squared is going to be minus 9, because the I squared is minus 1. Alright, and then that cancels with that, and that cancels with that, and we're just left with minus 9. Okay, and then we can say z is the minus b plus minus the square root of minus 9 all over 2 times a. So square root of minus 9 is 3i. So we've got 2 solutions. Let's do the one with the minus. That'll give us minus 2 minus 6i, and then divide that by 2, you get minus 1 minus 3i. And then if that's plus for the second solution, that'll cancel with that. And we're left with minus 2 over 2, which is minus 1. So those are the two solutions. Part C. We need to find the integral of the product of two functions here. So that's when we're likely to need to use integration by parts. And we'll have to integrate one of the functions and differentiate the other. So let's think about which one would be easiest to do. We can differentiate arctan x, but integrating it is a bit harder. Now you might know the derivative of arctan off the top of your head. If you don't, it is actually on the formula sheet. You'll find that on there. So if a equals 1, this becomes integral of 1 on 1 plus x squared dx equals arctan x plus c. So the derivative of this will be that. Okay, let's apply integration by parts to this, and we'll be integrating the x and differentiating the arctan. And now we need to think about how we're going to do that integral. I'm just going to copy this so I don't have to keep writing it. And this might be the hardest part of this question, is just figuring out how we're going to transform this fraction so that we can actually integrate it. So the way that I thought about it was, like, it would be really nice if we had 1 plus x squared up here instead of just x squared, because then we could cancel it with 1 plus x squared on the bottom. So what if we turn this x squared into 1 plus x squared minus 1? And then this becomes, like, you can split it up into 1 plus x squared over the 1 plus x squared minus 1 over 1 plus x squared. And then the 1 plus x squared over 1 plus x squared is just 1. Well, that's great now, because we can integrate that quite easily. The 1 becomes x, and then this is just our arctan x again. And I'll just put the plus c at the end. And I'll just put everything over 2 there, because you've got the half on all those bits. There it is. Part D. So to work out p of alpha and p prime of alpha, we need some way of writing p of x that shows that it's a multiple of x minus alpha squared. So let's just say it's x minus alpha squared times whatever, and we'll call the whatever q of x. And then we can say p of alpha is alpha minus alpha squared times q of alpha, and then this makes 0, so that's 0. And then let's differentiate this. You'd have to use the product rule, because you've got that times q of x. And let's differentiate this one first. That'll make 2x minus alpha, and then times the q of x. And then you've got this times the derivative of that. And then we can try finding p prime of alpha. So I'm just sticking alpha wherever x was in here. And then that's 0, so that whole thing is 0, and that's 0, so that whole thing is 0, so 0. And that's it. Part 2. So let's think about what we actually proved in part 1, because that's going to be important for this one. We said that p of alpha equals p prime of alpha equals 0 when we're in this situation that we've got a factor of x minus alpha squared. So another way of saying that is that alpha is a root both of the original polynomial and its derivative. So if we can differentiate this and work out the roots of p prime of x, and then see which one is also a root of the original function, then we'll have found our alpha. So let's differentiate this. And then let's try to factorize this so we can figure out the roots. So we've got a common factor of x in each of those terms. And then you can use the quadratic formula to factorize that, or you can do the thing where you do 4 times 2 is 8, and then you have to think of two numbers that multiply together to make 8 and add to make minus 9. So that would be minus 1 and minus 8. And then x times 4x minus 1 minus 2 times 4x minus 1. So that makes x minus 2 times 4x minus 1. So now we can see all the roots from this. You've got the 0 from there, you've got x equals 2 from there, and x equals a quarter. And those are the 3 roots of this. So we just need to see which one is also a root of the original function. So let's try p of 0. If we plug 0 in, all of that bit is 0, and then it's just 4. So that one doesn't work. That can't be our alpha. Let's try 2. So that'll make 16 minus 24 plus 4 plus 4. That actually makes 0. So that will be our alpha. And I'm not sure what a quarter makes if you plug it in there, but you can see that it's not 0. I would just do that on the calculator. So that's our answer. Okay, that's it for question 12, but stay tuned because next time I'll be going through question 13.